Hi, everyone. If you were here for the Glow talk, this is kind of looking at the front end part of the problem, where they're looking at the back end part of the problem, but otherwise they're very complementary kinds of techniques. So we're here to talk about this kind of cool compiler transformation called graph program extraction in the context of Swift for TensorFlow. And first I thought that many of you may not be very familiar with what is a machine learning framework. And a machine learning framework like PyTorch or TensorFlow or these kinds of things, on the one hand, is all about making some model run on an accelerator, okay? And it's all about finding some way to get some cool math tensor-based computation running on a high-performance accelerator. This is the Google TPU, but there are lots of them. And the interesting thing about this is that there are many kinds of devices to support, everything from mobile devices, really big data center accelerators, CPUs, GPUs, this whole spectrum. And there's also a lot of different kinds of computation. Some of the most interesting computation today is involving sparse computation, recurrent models, and a bunch of other more dynamic constructs that are coming into the machine learning community. So for the purpose of this talk, one of the most interesting questions that a ML framework has to solve is how do you take that tensor computation out of the program that the user wrote and allow a very high-level programming model while still being able to extract that and run that efficiently on an accelerator. And there are two major approaches for doing this if you look across the industry. The first is called eager execution. And if you think about this through the lens of saying, like, pretend we're targeting a single GPU, for example, what you do is you define a type, like a tensor type, and you put a bunch of methods on it. Each method launches a CUDA kernel. And so here we have some tensor operations like reduce sum, which does a reduction, or random uniform, which computes a random tensor. And each of these would launch a CUDA kernel. You overload the plus, minus, and other operators, and they also launch CUDA kernels. And it provides this very nice and simple programming model that's very approachable and understandable by even non-experts. So the great thing about this kind of approach is you get a lot of usability benefit out of it. If you do something wrong, you get a stack trace right out of the function call in question. It's very easy to understand, and it's really flexible because you can do arbitrary computation, arbitrary dynamic behavior in your program. The problem with this, though, is that if you look at this, the compiler in the backend infrastructure only has the ability to see one op at a time. And so, as you learned in the previous talk, that is very limiting for performance. Also, when you start talking about very large-scale accelerators, we're interested in things that are, current hardware has 100 petaflops in a box, for example. This can be very limiting to utilize that. So there's a second approach, and the second approach is called graph building, generally. This is like using IR Builder to build up a graph, which you then run manually. Graph building is really great because it gives the accelerator backends the ability to do optimizations and fusion and all kinds of different important performance-enhancing transformations. And so this is really awesome for graphs. But the bad part about this is the usability side of this is really problematic. And it's problematic for a whole bunch of different reasons, particularly for advanced models that need control flow, side effects, other things like that. And this is problematic not only because error messages and the user experience is bad, but also there's certain operations that you just can't put in a graph. Like researchers today want to be able to do tree recursive neural nets where you're walking binary trees, you're looking things up in hash tables and doing other things that you can't put in a graph. And so graphs just can't express these computations. Now, there are a bunch of other hybrid approaches and other things, but they all have fundamental trade-offs in what they're doing. And so the quest that we're on, the purpose of this talk, is to say, how do we combine the usability of eager mode, that very simple API, easy to understand programming model, flexibility, dynamism, with the performance and deployability of graphs? Because we really want both, right? So that's where Swift for TensorFlow comes in. And so this project is an open source project. It's really looking for like pushing limits of the programming model of using machine learning frameworks. And the number one thing we're driving for is usability. And so we want the best-in-class usability, which includes the eager-style programming model and many, many other things, for example, statically detected errors, but we don't want to compromise performance. And for me, I think the way I look at this is there's a huge number of new accelerators coming, but flops don't matter if people can't use them. And a lot of the people that want to be able to program these accelerators are machine learning experts. They're not compiler and low-level performance experts. So I'll give you a quick overview of how this works. So if you look at the Swift compiler works like many others. It starts out with a parser, it does type checking, it then has this high-level SIL optimizer, And if you run a Swift for TensorFlow program through this at 0, for example, it just runs. Each of these ops that you would call end up being dispatched one by one. But today we're here to talk about this thing called graph program extraction. This is effectively a new phase that gets dropped into the compiler that automatically looks at code through static analysis, extracts a graph, for example, with TensorFlow, and then allows you to deploy this and do high-performance optimizations that we will not be talking about today. So to talk about this more, I'd like to invite Mingsheng, one of my colleagues, up to describe this now.
Thank you, Chris. So to introduce graph program extraction, let's take a look at an example program. Here, the user starts by writing some tensor computation. We designate the magic syntax tf_up to represent any operator you can run on TensorFlow. Of course, user can write any host logic, like printing messages. User can also write control flows, like writing a loop over more tensor computation. Now, given this program, how do we execute it? One option is, as Chris introduced earlier, through eager execution. In that mode, we dispatch each tf_up individually to TensorFlow. And if needed, we get the results back to the host. So eager mode is really easy to work with. But if you want higher performance, then what you want is to be able to dispatch a larger chunk of tensor computation all at once. And the first thing there is that we need to extract a computational graph that involves tensors and tensor operations. And then we can launch it onto TensorFlow, just like launching a GPU kernel. TensorFlow supports other device types, but just for familiarity of the programming model, for now we can think of it as a GPU accelerator. How do we do this? Let's first take a look at what you get out of the graph program extraction. So we first mark those statements and control flows that we can run in the graph. Then we create a graph function with those statements and control flows. And then we can rewrite the host function. We clean up the code, and we insert asynchronous start graph computation call at the beginning. And later we can wait for the graph, just like launching a GPU kernel. Right, so that's what GPE can do for us. Let's now dive into how GPE works. And we're going to break it down into 3 major steps. We first mark the relevant instructions for graph execution. We then partition the host function to generate that graph function. And finally, we can lower that graph function to something that TensorFlow can execute, and we rewrite the host function to call into the graph. So let's look at these steps. Here, our compiler analysis and transformation works on top of SIL. That's the Swift Intermediate Language. It was introduced by Joe Groff and Chris Lattner a couple years ago in a dev meeting when Chris was still an Apple intern. So here, you see we're using the same running example. And it's in the CFG representation. We're using SIL code with some simplification. You may recall, we started with some tensor computation, and then there's a conditional branch running some printing message logic on the host, and it's followed by a loop with more tensor computation. The first step is we first mark those tf_up instructions. You may recall that this magic tf_up, so these new types of instructions, they are the operations that must run in TensorFlow. So they form anchors in the graph function we're about to build. Next, we define tensor start point to be the first tf_up instruction. We also define tensor endpoint. Usually it points to the last tensor instruction, but we also require that the endpoint post-dominate the start point. So in this example, it points to the first instruction in the exit block. And together, the start and endpoints mark the boundaries of the tensor program region. And from that region, we will later extract the graph function. The next step is we're going to transitively process all of those marked TF ops and their operands. So we start with W0, then we also mark X. When we mark an instruction, we also mark the parent basic block. This is how we form the CFG structure of the graph function. So when we mark the loop body, we also need to process its predecessors transitively to see what other blocks we need to mark for the graph. In this case, the predecessor is the loop header, and we need to do control dependence analysis. So we know that the loop body does not post-dominate the loop head, because loop head can go directly to the exit block in some cases. So as such, we know the loop body is control dependent on the loop head. So we need to think about how to execute the terminator instructions of the loop head. That's the highlighted conditional branch here. There are two options. We can still run that conditional branch on the host and send its output to the graph, so we can run the loop body in the graph. Or, as a more performant option, we can run that conditional branch itself in the graph. And that's what we chose. Now, since the graph can only execute tensor operations, this involves promoting the scalar value b to a tensor. And that's what we call scalar promotion. We now recursively go up, and we see that the loop header predominates and therefore is not control dependent on its predecessor. So we don't need to mark the loop preheader. And similarly, we don't need to mark the print block. And we keep going with this algorithm, transitively mark the instructions and the operands. We find that all of those scalar instructions related to loop counter, we can promote them to the graph. We keep going, and we mark W1 and W2 as well, and that completes the marking pass. So just a couple observations. By now, we have marked the entire loop to be ready for graph execution. Also, if you look at the terminator instruction at the entry block, the conditional branch, it is not marked. And that's again because the print block is not marked for graph. It stays on the host. Okay, so having done with marking, we're going to do partitioning. The first step there is we're going to establish the CFG structure of the graph function by looking at what blocks we have marked on the host. Now we're going to clone and map over the marked instructions. For the entry block, because the terminator conditional branch is not marked, we need to synthesize an unconditional branch. And we connect it with the immediate post-dominator in the graph. And in this case, we're connecting that entry block with the loop preheader. And this is how we can slice the print block out of the graph execution. This kind of program slicing behavior is our intended and desirable behavior. And by the way, this is the payoff of the earlier control dependence analysis we talked about during the marking phase. We keep going, mapping and cloning over the other instructions, and we finished building the graph function. Now we're going to rewrite the host code, remove the code we have moved over to graph, and at tensor start and endpoint, we insert the calls to call into the graph and wait for the execution to return. Again, the graph execution is asynchronous. Having constructed the graph function, we can then lower it to a graph format that TensorFlow can support. This process is mostly mechanical. It's got some interesting details, but unfortunately, we won't have time to cover today. Once we got this TensorFlow graph, we can store it as a serialized string embedded into the binary. So at runtime, we can deserialize it and send that graph to TensorFlow. One of the nice things about our design is its support for flexible communication between the host and graph functions. So we already talked about how the host can wait for the graph execution to finish and get its return tensor. But in addition, when these two functions, host and graph, are running concurrently, they can also communicate through sends and receives. So as an example, suppose user have written some tensor computation that produces tensors x and y on the accelerator in the graph function. Now we want to use them on the host because Atari game simulator only runs on the host. How do we deal with this? We don't want user to explicitly write sends and receives. That kind of programming model is not very usable. So the idea for compiler to automatically do this is it looks at the host function Atari simulator. It sees that the operands x and y are produced by the graph. So then it's going to introduce send primitives to the graph and the corresponding receive primitives on the host side. Conversely, when we want to send the tensor z from host back to graph, we insert the send and receive primitives accordingly. Now, so far, we've been pretending that TensorFlow is a GPU accelerator. In practice, it's a distributed system, and you often feed data and run a machine learning model on a cluster of machines. Each machine is attached to one or multiple accelerators. And you often run different subprograms on these individual accelerators. So now, when we are given a graph function, we need to do something called device partitioning to split that graph function into a set of per device or per accelerator functions. And we can insert sends and receives if needed to do cross-device communication. This device partitioning supporting compiler is very similar to the host graph partitioning that we just covered. So having talked about the compiler design, now we can look at what kind of programming model we can build on top. So far, our code looks like what's on the top. It uses very low-level primitives like the tf-up magic. It's like tensor assembly. So we don't want our end users to be limited to those primitives. We want our users to be able to write something that's more at the bottom. Beautiful Swifty API. How do we do that? First, we introduce a tensor struct. It is generic over a tensor data type, so you can define an integer tensor or a float tensor. The struct itself wraps an underlying untapped typed tensor value. You can think of it as a C memory buffer. Based on this, we can add static and member methods to support different kinds of APIs. That's how we can support matrix multiplication, addition, and other things. Now, our end user will be able to write something that's like at the top. And our compiler will desugar it all the way to the bottom by inlining the calls and scalarizing the structs. And that prepares the code to go through graph program extraction. So this is supporting abstractions without runtime overhead. And similarly, we can support generics by specializing them at compile time. We can also support higher order functions by inlining them as long as the closures do not escape. So with all these nice abstractions, we're able to build beautiful APIs. For example, here, the dataset abstraction allows us to read and process the training data and then feed them on a per batch basis to a training loop, where in the loop you can do various tensor computation. And often it's the case that the data set and processing is done on a set of devices like CPU, and then the data gets transferred to another set of GPU or TPU cluster servers. So this kind of device partitioning is all done automatically by the compiler. So this concludes the deep dive of our graph program extraction and associated programming model. Now, our set of algorithms can work with any SSA-based IRs. Also, the kind of graphs that we can extract need not be limited to TensorFlow graphs or even machine learning. We believe as long as in your domains, you have the need to automatically extract or slice out a particular kind of computation that you can express in the form of data flow graphs, then you may be able to use this set of techniques. And you can run them on your own accelerator devices. So back to Chris.
All right. Thank you, Mingsheng. So that's a quick deep dive into one piece of the Swift for TensorFlow project called Graph Program Extraction. The project itself is quite a bit bigger than this. There's a bunch of really cool APIs and high-level things for working with TensorFlow specifically. In case you hadn't noticed, the machine learning community is very attached to Python. And so we've gone and directly integrated Python right into the Swift language, so you can directly call Python APIs, which is really nice. A major other focus is automatic differentiation. We're actually adding first-class support, language-integrated automatic differentiation, which is really cool. If you're interested, you can Google for this manifesto talking about how this is going to work. But Swift for TensorFlow is open source. If you want to read more about it, you can go on the GitHub page. We have a bunch of technical documentation and other white papers, and we'd love for you to get involved. Thank you.
All right, we have a little bit of time for questions. Right over there.
Great job.
Hi. In the program extraction part, you mentioned that it needs to basically there needs to be a post-domination of the graph extraction part. If the counterflow is weird and there are like multiple returns or like loops that are not natural, what do? You try to transform the graph into something you can process, or you use some other tricks or something like that?
Yeah, so that's a great question, how we handle arbitrary control flow. So overall, there are two sort of techniques, and we implement both. The more optimal technique is what we presented. If you can detect the shape of the control flow and you can lower sort of the conditional branch and you put it all to the graph, then you get a really optimized form. But you cannot always do that. So we fall back to just running whatever, let's say, switch case. You evaluate the switch statement on the host, send the case number to the graph. And then essentially it's like going to a particular block. And then essentially in that case, the host can drive the accelerator computation. So the control flow in the worst case all runs on the host. But one thing to notice, even in that case, you don't have to get all the tensors transferred back and forth. You can leave the tensors on the device, on the accelerator side. And you may need to get some pointers back and forth.
Yeah, so I would also say the presentation was a little bit oversimplified in several ways to fit time. We can actually insert endpoints on multiple different exit paths, things like that. Swift also has a number of exit paths out of the function, for example, when traps happen. And so we actually do the analysis on a pre-sliced version of the CFG, like a, not actually sliced, but a conceptually sliced version that eliminates all those exit branches and stuff like that. There's some more details that go into it, but you're right.
Okay, so I'm very excited by this. I've been trying to, so one thing I've been trying to do is start up a machine learning group in C++ as well too. And looks like something like this can fit on top of that, the graph extraction. It's really a graph programming language, as you rightly pointed out. One thing I'm interested in seeing is, are you able to do things like kernel fusion of both the node and the overhead? I saw that in the previous talk in the IR, they can do essentially kernel fusion. This is one of the most important aspects for things like tiling.
Yeah, so the way to think about this is very much a front-end kind of a problem, tackling programming model and abstractions for programmers. We are almost completely independent of the actual graphs. Like, we don't actually care what the labels are, if it's an add or convolution or it's a Bitcoin mining thing or whatever. Like, we don't really care. That's up to the back end. And so the back end then gets the operations, interprets them, can do fusion, other things like that. That's a mature field, and there's a bunch of work going on that's new and other systems. And so for this work, it's completely independent of those kinds of transformations.
Just to add,
this would also fit really well C++, incidentally. I mean,
yeah. And to add one thing on top, this could be thought of as an enabler to fusion, because if you only run each TF up in the define by run mode, you're not going to talk about kernel fusion.
All right, that's all the time we have for today. Thank our speakers, and if you have any further questions, you can ask them after the session.